Elements of sampling designs. Our choice of sampling design is driven by management objectives and sampling objectives. Sampling design encompasses the practical components of a sampling endeavor: what we measure, how we measure it, and where it's measured. If we look a little more closely at these two types of objectives, we can see that a management objective has very specific criteria about a desired state of change or condition for a site or a population of interest. Compare that to a sampling objective. Sampling objective includes a statement of confidence and a statement about the precision of the estimate that is desired through the sampling endeavor. These two kinds of statements are very important in the selection and determination of our sampling design. So what are the elements of sampling designs? We need to identify very clearly the population of interest, the attribute to be measured, and the method that we use to measure that attribute. We have to select the type of sampling unit and clearly specify the dimensions of the sampling units. How we position these sampling units in the landscape is very important, as is the sample size or number of sampling units and the subsampling intensity or the number of observations within each unit. When we're talking about the population of interest, we may be interested in sampling in a relatively large area, such as across a state or region, or we may be focused on a particular vegetation type in a management unit. Sometimes we delineate the area and will sample anywhere within that area, or we may select certain key areas that share a particular characteristic and measure within those, such as an ecological site. Now, the attribute to be measured is very closely determined by the management objective. And in vegetation measurement, we have several different attributes that we tend to focus on. And there are multiple methods available to measure these attributes. The selection of the method is always case-specific, influenced by our objectives and by practicalities of cost and the amount of skill and training that is required. We can see from this table here that there are multiple approaches to measuring each of the attributes that are described here. And both a study of the attributes and the methods will be presented in subsequent lessons. Sampling unit types vary between points, transects, quadrats, plots, individual plants, or plant parts, and sometimes we use combination sampling units. For example, in this diagram, in this photograph at the lower right, we see two women who are measuring along a combination unit type. This is a transect, and they have quadrats that they're measuring within along this transect. So they would use multiple quadrats on a transect, and that is a combination unit type. Our choice of unit is closely determined by the attribute. Some attributes, such as production, can only be measured using one type of sample unit, such as a quadrat. Cover, on the other hand, can be measured with points, lines, or quadrats. And again, the sampling objectives and vegetation characteristics, such as the amount of patchiness, heterogeneity, and also variation in plant size, can determine the kind of sampling unit that we use. The dimensions are important because they can influence the precision. We're talking about transect length or quadrat size and shape. And in general, as the vegetation heterogeneity increases, we will use longer transects and more rectangular quadrats in order to improve the precision of our estimate. Let's look at an example of transect length. In this case, we have three diagrams that represent different vegetation types. On the left, we have a very homogeneous or evenly distributed grassland. In the middle, we have a patchy grassland with scattered shrubs, and on the right, we have a woodland with scattered trees. If we use relatively short transects, we can see that in the homogeneous grassland, the transects do a good job of incorporating the variability of the vegetation, and so there's little variability between those sampling units, so it's relatively precise in that vegetation type. This is not true for the other two vegetation types because we have some transects, a few, that have a lot of vegetation and then several that have none. In this case, we would use longer transects, and we find that as we increase the length of the transect, we cut across the variability of the landscape and we get greater precision between our sampling units. In the woodland situation, we would go with an even longer transect in order to better incorporate the variability of that system. Let's look at the influence of changing the size of quadrats. So here we're going from relatively small square quadrats. We can see that we have a number that are empty and then several that are quite full. So there's not very good similarity between those sampling units. As we increase the size of the quadrat, we incorporate more of the variability of the landscape, and we have more similarity between our different sampling units with larger quadrats. So we have greater precision overall. Now, if we consider shape of quadrats, they can be circular, square, or rectangular. These differ in the amount of perimeter to area ratio, with circles having the lowest and rectangles having the highest perimeter to area ratio. In general, the attribute of interest and the vegetation often drives our choice about shape. Let's look at what happens if we alter the shape from square to rectangular. In this situation, we see that we increase the precision as we go to more and more rectangular quadrats because it incorporates more of the variability that is inherent in the area within each one of the units. Now, how we position our sampling units is also important. We can use different sampling schemes such as random sampling, stratified random, systematic, selective, and others, and this is something that will be covered in more detail in another lesson. However, the orientation that we choose for our transects can have great influence on precision if there is a gradient involved. Here we see an example of a vegetation diagram in which there's a gradient. There's definitely more plants on the left than there are on the right side of this vegetation diagram. If we orient our belt transects so that they go against the gradient, what we have is some transects with a lot of vegetation in them and some with very little. So there's not much similarity between them, and we have higher variation among the units. On the other hand, if we reorient the belt transects so that they run with the gradient, we see that we have greater chance to incorporate regions of low and high variability inside a unit. And by doing that, we have reduced the variation among the units, and so this increases precision. What about subsampling intensity? This is the number of units or of observations that we take within each sampling unit, and it influences the precision because we have more information that we gather per unit. Here we see an example with 3 different transects, and the only thing we've changed is the number of points that we're collecting per transect. By increasing the subsampling intensity, we see that the standard deviation decreases, the standard error decreases, and so we increase precision because we have more information with increased subsampling intensity. Now, sample size is a very important component of all sampling designs. We see that in general, if we increase our sample size, in this example, we're going from 3 transects to 6 to 9, we decrease the standard deviations and the standard errors, and so we have better precision. Why is this? In general, by increasing sample size, we reduce the influence of outliers. For example, if we look at rolling dice and using 3 rolls versus 6 rolls, by chance we could have some outliers, and that's going to result in a relatively high standard deviation relative to the mean. If, on the other hand, we add more rolls, we can reduce the influence of these outliers and essentially lower the standard deviation or increase the precision. Another reason that sample size increases precision is the influence it has on standard error. This is simply mathematical. Even if you hold the standard deviation constant, the standard error is defined by the standard deviation divided by the square root of the sample size. And simply by definition, if you divide a number by a larger number, the resulting value will be smaller. So the standard error is smaller if you have a larger sample size. As a general rule, we need to increase sample size when the inherent variability of the vegetation is high. Our sampling objectives, the components, the confidence level, and the desired precision, greatly influence our decisions about sample size, our requirements for sample size, as does the inherent variability of the population. What we will do is conduct some pilot sampling and then use the sample size formula to estimate the necessary sample size. There are several different types of sample size formulas, but they all have common elements. They include a component about the desired confidence level, the range of the estimate around the mean, and the observed variability. In this case, the t-squared represents the desired confidence level, the s-squared represents the precision of the estimate that we got from the pilot sample, so the observed variability, and the e-squared component in the denominator represents the desired precision that is set by our sampling objectives. What happens if we calculate a sample size and it's larger than we can practically sample? One thing we can do is change the sampling design components in order to reduce the variability. So we would look at the type of sampling unit, how they're oriented, possibly the length or the shape of the sampling unit, and see if by changing that we can increase our precision. Other choices that we can make are to change the confidence level and also to change the acceptable range around the mean. So we can alter our sampling objectives if that's the only way that we can reduce our sample size. So in conclusion, sampling design is driven by management and sampling objectives. It incorporates numerous elements, and careful selection of design balances a trade-off between the need for precision and confidence with practical considerations of the time and the cost that's involved in sampling.